Okay, so part 3, I guess, now, aren't we? Page 4, but part 3. So we just finished up talking about, or we've introduced steady flow control volume first law. All right. So, with that in mind, let's talk about the energy of mass crossing the boundary. Now, before we do that, we might introduce our good friend here, the conservation of mass. Had some scratch paper there. I printed on the back so it wasn't scratch paper anymore. So we talk about, if we introduce, let's say also, the conservation of mass principle. So remember back to our outcomes for the course. We said, well, you're going to need to be able to use the first and second laws in conjunction with other laws, equations, and principles. Well, ideal gas law is one of those. Conservation of mass is one of those. So if I'm dealing with air, I can use ideal gas law, or anytime I'm dealing with control volume, I may need to employ the conservation of mass principle. And the conservation of mass principle is also it's conservation law. It's an in minus out equals change idea. So we say, well, if I add up everywhere mass comes into the system, add up the mass flow rates coming into the system, subtract everywhere that mass is going out of the system, subtract the rate at which it's going out, that's going to equal the rate of mass change for my system with respect to time, dm dt. And again, for if it's steady flow, then we're just simply saying that the total rate of mass in is going to equal the total rate of mass out. So if I've got multiple inlets and multiple outlets, I just need to add up the rate at which mass comes in from all the inlets, and that's equal to the rate at which mass goes out at all of the outlets if it's a steady flow. If not, the difference between these will represent the rate at which mass changes over time. Okay? Now, for one inlet and one outlet. And what I like to do is call those 1 and 2. Inlet being 1 and outlet being 2, then the m dot in is just going to be m dot 1. The outlet is just going to be m dot 2. There's no reason to differentiate these. These are the same. Right? If it's flowing steadily, the in is equal to the out, so 1 is equal to 2. And again, what we normally do is we don't even differentiate them. We just say that's m dot. It's the same mass flow rate throughout the system. If it's one inlet, one outlet, that's flowing steadily. Okay? Okay, so how do we find this m dot? Well, any m dot, we can always find m dot as the density times what we call the volumetric flow rate. For us, that's v dot. Some texts will use a q, especially a lot of fluid mechanics texts will use q for flow rate. We use q for heat, so that doesn't help us. Right? So this text and some other thermotexts will use a v dot here if they talk about volumetric flow rate. If you don't have the volumetric flow rate, maybe you have the cross-sectional area of the conduit and the average speed. And recall, our friend, the specific volume, is the reciprocal of density. So anywhere I've got density, especially if I've got like a vapor or a gas, I might have the specific volume. And so they're interchangeable. I'll just use the reciprocal of one in place of the other. The product of area and speed, again, gives me the volumetric flow rate. So various ways you can compute m dot. Which one to use, I don't know. You have to look and see what you got. Look at the units. The dimensions will help you. This is mass per time. This is volume per time. This is mass per volume. You guys get the idea. Right? Okay. How does this help us, Steve? Well, remember back here, we're talking about a control volume. Control volumes are things where mass crosses the boundary. So if mass is crossing the boundary, I need to make sure that the mass is actually conserved. And it's real simple if it's one inlet and one outlet. It's just the same mass flow rate throughout. So m dot is equal to rho AV, or AV over little v. Okay. Again, depending on what I have there. Now, what does this do for us? Well, if we look at E dot mass in. Okay? So if we look at the energy of mass coming into a system, well, what I can do is I can take the mass flow rate, because this needs to be energy per unit time, and that mass as it comes in is going to have its own internal energy. This is energy per mass. If I multiply this is energy per mass multiplied by mass per time gives me energy per time. So that makes sense. So again, that mass as it comes in is going to have its own internal energy. It's going to have its own kinetic energy. And it's probably going to have a negligible amount, but it's still there, potential energy. And we've talked about this in class before. If it's stationary, if the mass is not moving, these are the energies that it has. Okay? But since it's moving, something causes it to move. It doesn't just move spontaneously. Something pushes it. Something forces it to move. And what causes it to move is the pressure of the mass upstream pushing the mass downstream out of its way. Pressure by itself is not an energy term. So what we do is we say, well, if I apply that pressure through the volume, right, pressure times volume will give me an energy term. And we normally don't, we could go look up a U value and then take the product of pressure times volume and then add them all up, and that would be okay. But normally what we do is we say, well, we have this term enthalpy. Enthalpy, the H value, is the sum of U and PV, and that's just a quantity that is defined for us. We don't have to, so what that means is I don't have to take the product of pressure in the specific volume and then add it to the U value. If I've got tables that have got H values, and most of them do, ours do, that's already done for me. So the energy of mass in, or out, by the way, the energy of any flowing mass is going to be the mass flow rate times the enthalpy plus the kinetic energy plus the potential energy. Okay, so we get back down into it. Again, is for steady flow control volume with one inlet and one outlet. And this is the most common type of steady flow control volume that we will deal with. If that is the case, then I can group these two together. Right? Well, let's just kind of group them all up. We can rearrange these, as long as we preserve the sign, we can rearrange these other power terms. So I can say the heat rate in plus the power input minus the heat rate out minus the power output, plus then, instead of saying E mass in minus E mass out, I'm just going to say, well, it's the same mass flow rate at both the inlet and the outlet. So then all I have to do is take the enthalpy at the inlet minus the enthalpy at the outlet, plus the kinetic energy at the inlet minus the kinetic energy at the outlet. And then most of the time we just neglect the potential energy because it's normally tiny compared to these other terms, but it's still there. And if it's flowing steadily, that whole sum is set equal to 0. Okay, and so this is the most common form of the first law that I will use for control volume. So this is the most common form of the first law I will use for closed systems. This is the most common form of the first law that I will use for control volumes. If I have more than one inlet and or more than one outlet, then I have to do this m dot times the kinetic, this term here, this m dot times the enthalpy plus the kinetic energy, and maybe the potential energy at every inlet. I have to add this at every inlet, and then subtract this at every outlet. But if it's a single inlet and a single outlet, it does simplify a little bit to this quantity here. And again, our goal, whether it's this one or this one, whether it's a closed system or a control volume, our goal is to figure out which of these terms do I need, which ones are important, and simplify from there. Okay. Crash course in the first law very quickly. Now, within the first law, another learning objective is the idea of a compressible system. If the system can be compressed or if it can expand, right? Let's say this. If the volume initially is not the volume at the final state, this does not happen spontaneously. The volume of a system does not change spontaneously. To get it to happen, to get that volume to change, you have to do work to the system. And that work comes in the form of what we call the boundary work. If you'll integrate from the initial volume to the final volume, pressure with respect to volume, you're measuring the work output. If you want to find the work input, the compression work, you need to switch the sign on the integral, or just understand that when I compute the work out, I'm going to get a negative quantity. So if I get a negative quantity here, it's just telling me that I'm actually compressing the system, I'm putting work into it. If the system's expanding, then it's putting work out. The system has to expand into the surroundings. The system's doing work to the surroundings. That's work out of the system into the surroundings. And the opposite is true if we're compressing the system. So if I'm compressing the system, the surroundings is putting work into the system, the opposite of work out. Okay? All right. There are other types of work. We could have electrical work. All right, we've seen that. Electrical power. Right? Electrical power is W dot sub E is equal to the product of voltage and current. Which a lot of times we just write that is V times I. Okay? If you want the electrical energy, that's going to be the integral of electrical power with respect to time. And we're only going to deal with constant voltage and constant current in this course, but we've seen that in the homework. I think that's shown up on the exam here or there. That's completely fair game. I've not written the final problems, but just throwing that out there, that is possible. So there's different ways we can find work. Heat, if it's only a first law problem, heat is probably something we're solving for. But if it's a second law problem, we've got other tools for finding that heat transfer. Okay, so let's see what else about, I think that's chapter 4 and 5 in a nutshell, and 3 as well. I think now that brings us up to chapter 6, where we introduce the second law, and when we talk about the concept of a heat engine. Right? The heat engine is this device where I've got a boiler absorbing heat from a high temperature source. That's going to feed a turbine or a turbine. That turbine's going to extract a power output. And so we'll say Q dot H. From there, working fluid, typically water, is going to go into a condenser. The condenser is going to reject remaining heat to a lower temperature. And then somehow we've got to increase the pressure because I want high pressure here. Normally how we increase the pressure is we get it down to a liquid form in the condenser. We put just a little bit of power input to a pump. So just a little bit of power input to a pump. That pump supplies a boiler and the cycle repeats. Okay? So the first law for this system says, well, if I add up all the energies in, subtract all the energies out, you end up with, let's just write it this way. Let's say that Q dot H minus Q dot L minus I'm going to say the net power output, the difference between this and that. And because it's a cycle, that's going to equal 0. Right? And so normally we have this quantity we call the thermal efficiency. I'm going to have to pick up there on the next one. Lab pop in.